Okay, so let's start the second quantum session today. So I count the previous one is also quantum session. So second quantum session, and the first speaker is Luo Enkian, Justin Raises, and Mark Zandri. And Justin will talk about this hard quantum extrapolation. So please start.
All right. Thank you for the introduction. This is, as you mentioned, a joint work with Loan and Mark, and here's the clicker. Okay, so everyone probably recalls that one-way functions are minimal classically. So they're equivalent to signatures, zero knowledge, key encryption, and are implied by basically anything you can think of. And generally, we can think of two kinds of assumption styles. We have our search type assumptions, like commitments or signatures, where, for example, in a signature, given a public key, you want to find an accepting signature. We also have decision style assumptions, which are like encryption or OT, decide between encryptions of two different messages. And there are prior works that have shown that both of these two styles imply one-way functions. Now, when we move to the quantum setting, we can do a similar breakdown of search versus decision, but currently the question of a minimal quantum assumption is still not entirely understood. We're getting much better at it, but it's not fully understood. And one of the things that really changes in the quantum setting is we now have this notion of quantum money in the search style assumption. I'll go into this a little bit more in a minute, but an interesting piece of the quantum setting is that one-way functions are not necessarily implied by commitments. So they're no longer minimal. Now, we've seen that decision-style assumptions, such as encryption, zero-knowledge, OT, and so on, do, however, imply commitments. Not necessarily one-way functions, but at least commitments. And of course, commitments also imply many of these primitives, such as zero-knowledge, OT, MPC. But currently, there's not really a lot of work on search-style assumptions and commitments. There's a disconnect there. And in this work, what we do is we connect search-style assumptions to commitments. We show that specifically, public key quantum money implies commitments. Now, this might seem a little bit of an odd statement because public key quantum money is this really strong primitive that we only know how to construct from crazy assumptions like I/O. But you'll agree that it's nice to know that such a strong assumption does imply something very weak. And in addition, we also have some other primitives which are also search style primitives that also imply commitments. And we'll see why we're grouping all three of these together as we go on. So let's quickly mention the Impagliazzo-Luby proof overview. So we're going to start with our search type assumption. This might be a signature, a commitment, or weak coin flipping. And then they construct this problem, which they call universal extrapolation. And then this unifies all three of these search type problems. And then they show that this implies one-way functions. OK, so what is universal extrapolation? The idea is there's some arbitrary circuit that efficiently samples from a bivariate distribution. So it's going to output some bivariate distribution, x, y. And then you sample a random x that's drawn from the marginal distribution of x. And given this x, the task is to find y. So in particular, the adversary needs to find a given x, needs to essentially produce a sample from the circuit. And you can construct this from signatures, commitments, or coin flipping, where you consider x to be the public key. This is the information that you're given. And then Y, what you're trying to find, is the private key, or maybe the randomness. In this work, we propose a generalization of this notion to the quantum setting. We actually propose a couple of different variants of this. The first one is classical to quantum extrapolation. The idea here is we're going to take an arbitrary unitary circuit that efficiently prepares a bipartite pure state. So in general, we can write this as a superposition over x of x tensored with some state that depends on x. And we can assume this is pure without loss of generality, simply by saying that this is what is output by the circuit, and eventually you'll see that we do trace things out. So that's how we can bridge the gap. So speaking of tracing things out, what we're going to do is we're going to actually measure this x. And this will collapse the state down to being just psi x. Then the task is to, given x, extrapolate that quantum state. So in particular, you want to take x and then find something that is close in trace distance to psi x. And we can actually construct this from public key quantum money, signatures, or two-message QKD. And here x is going to be the classical public key or transcript. And then y is going to be the private key or the quantum state. So for example, for public key quantum money, to break this, if you could break classical to quantum extrapolation, what you could do to break quantum and public key quantum money is you could take in a serial number and then find the money state. So you actually don't even need to clone. You just directly invert the money state. So as I just mentioned, all three of these things, including our main application of public key quantum money, imply hard classical to quantum extrapolation. Then we show that this implies commitments. I'd also like to mention that you can generalize this to clonable quantum extrapolation, where the difference is that this initial state here that the challenger is going to keep is actually a quantum state instead of being classical. And what we're going to do is we're going to clone it. Intuitively, this binds the adversary to solving a particular x. And then the task is given that cloned state, find psi x. And it turns out that you can also use this to construct public key or commitments. I'd also like to mention some related or concurrent works. So Chung, Golden, and Gray showed that distributional one-way puzzles, well, they consider distributional one-way puzzles, and that's actually very close to hard classical extrapolation. So this is like universal extrapolation, but with a quantum sampler. Then they also showed that distributional one-way puzzles are equivalent to one-way puzzles. This you can get some very nice picture of what's going on with one-way puzzles. Kabir and Dikshita also showed that one-way puzzles, again, this hard classical to classical extrapolation task, imply EFI or commitments. And then in a later work, they also proposed something they called state puzzles, which is essentially equivalent to our notion of classical to quantum extrapolation. And they also showed that you can get state puzzles, imply distributional one-way puzzles, which then if you follow the chain of implications, you get commitments. But they use a very different approach via state synthesis. So the advantages of this approach is that now you have hardness amplification for weakly hard extrapolation. The disadvantage is that it's a much more complicated construction. You get a larger efficiency and security loss. All right, let's just quickly go over what a quantum commitment looks like in its canonical form. So let's imagine we have two efficiently preparable pure states that are bipartite. They're split over two registers C and D. Alice can commit to Bob by taking her state and sending Bob the C register. So now the two are entangled. She keeps the D register as her opening register, and when she wishes to open, she sends it to Bob. At this point, now Bob has the whole state, and he can just check that the state was indeed psi B. So this is a commitment to B. Exactly, so he tests as if it's correct. And for hiding, we want that this C register should be indistinguishable between 0 and 1. And for binding, we want Alice to not be able to reveal a D register which would open to a different value than she actually committed to. OK, now that I've told you about canonical quantum commitments, let's talk about the actual construction. The idea is we're going to start off with, just say a commitment to 0 is going to be our minted state. So we'll sample S and psi S, and then we'll copy S into this commitment register. And then let's imagine that somehow we were able to produce the state S tensored S with the same weighting on each S. Now, this is perfectly hiding, because if you're just given the commitment register, then all you see is S with the same weighting. On the other hand, if all you have is the opening register, then in order to break binding, in order to map a commitment to 0 onto a commitment to 1, you'd have to go from S to psi S, which is exactly what we assumed was hard. OK, we're done, right? Unfortunately not. So in general, this above state might not be efficient to prepare, which is very unfortunate, because it would make our lives a lot easier. So the issue is that we need to actually hide psi S from the opener in order for us to say that it's hard to map S to psi S. We can't just throw it on the other side, because then we would have hiding issues. And so our idea is we're going to hide psi S from the sender by encrypting it. Now, unfortunately, this has its own issues. It turns out that if you're not careful about your encryption scheme and your psi S is in a bad basis for your encryption scheme, then just by encrypting psi S and sending the key to the other side, you actually break hiding. It's very interesting. So our idea is this is basis dependent. I'm not going to go into the details of how it is, but the idea now is that just take a random basis and measure in that basis. So we're going to pick a random basis, k, and we'll put k on both sides, the commitment register and the opening register. Then we're going to take a measurement of psi S, and we're going to copy that into the commitment register. On the other hand, if we want to commit to 1, we'll keep psi S over here, and we'll take a measurement of the 0 state. Now, intuitively, this over here, if this basis is really incompatible with psi S, then this should hide psi S from the opener. And so now maybe we can argue that going from S to psi S is hard, even with X. And in fact, we are able to show this. This requires a little bit of technical work. I'm not going to go too far into the details because I'm a little short on time. But the second part of this is we also have to show binding. Because note that we've measured psi S and put it over here. And we measured, in this case, 0 and put it over here. So why would these two states be indistinguishable? And what we have to do to show this is that we have to show that essentially for a random, appropriate choice of a random basis, these are actually statistically indistinguishable, at least weakly. And then you can do parallel repetition to amplify. So I'd like to mention that, intriguingly, even if you increase the design, say all the way up to Haar randomness, it's still not fully statistically hiding. You get something like, I think, 1/4 hiding. But I forget the details on that. You'd have to look at the paper. As a last question, I'd like to mention that third generalization of extrapolation to the quantum setting, which is fully quantum extrapolation. Before we had this classical input, quantum output task. Then we moved to a slightly quantum input, and again, quantum output. But by slightly, I mean that the quantum input was clonable. What if we just had a general quantum state? So, as before, we're going to have an arbitrary unitary that efficiently prepares a bipartite state. And here, both sides are going to be quantum. Now, when I write this, in order to make this make sense a little bit when you trace out one of the sides, we're going to write this in the Schmidt basis. So you can think of each psi x as orthogonal to psi x prime, and similarly phi x is also orthogonal to phi x prime. And the goal is to extrapolate psi x complex conjugate from phi x. Now, first thing, Schmidt basis is not unique. And it turns out that in order to have a well-defined search task, you actually have to take this complex conjugate. So we show that this ends up being unique if you do. Then we show that hard quantum extrapolations are actually implied by commitments. And also we show that this is a reasonable, it's actually a computational assumption rather than something that's statistically hard, because it's solvable in quantum p-space. Unfortunately, we don't actually know how to use this to construct commitments, so that's an open problem if you're interested. So just to remind you, we took a search style assumption, such as public key quantum money, and we showed that this implies hard classical to quantum commitment extrapolations. And then we took that and showed that it implies commitments, which of course gets you everything else in that equivalence class. And so far, it seems like commitments are kind of this best candidate for quantum minimal assumptions, both in terms of being useful and seem to be implied by a lot of other things. Of course, we also have this hard quantum to quantum extrapolations, which so far seems to be below commitments, although it's not immediately useful. And as I mentioned, very interesting open problem. Can we use hard quantum to quantum extrapolations to construct commitments? And coin flipping as well. How does this fit into the picture? Thanks.
Thank you for your talk. So we don't have enough time, so just we accept one quick question.
Thanks for your nice talk, Justin. My question is that you mentioned the slightly quantum to quantum extrapolation, and what's the level of it, say, what's the hardness level of it related to, say, EFI or puzzle or extrapolations introduced here?
Yeah, so this slightly quantum is the clonable quantum extrapolation. We actually do show that it lies here, so it does imply commitment.
It implies commitment and implied by CQ extrapolation?
Huh?
You say that it implies commitment and implied by classical to quantum extrapolation?
Yes.
Okay, thank you.
That's correct.
Okay, so you can ask a question later. So let's thank the speaker again. So the next speaker is Minky, and he's going to talk about generic lower bound. So please start.
Okay, thank you for the introduction. Yeah, I'm happy to give my first single assert paper. Today I talk about the quantum and classical generic lower bound for global link problems, like discrete logarithm or factoring. But I mostly talk about the discrete logarithm stuff because it is simple. Okay, the motivation of the research is as follows. What is the actual running time of all listers for running the Shor's algorithm to break discrete logarithm or factoring? It's practically relevant, and the recent estimation, among many, says that the Shor's algorithm actually solves a discrete logarithm problem or factoring in about 1 day, assuming many physical, but probably realistic assumption. It is much faster than classical algorithm, which require 5,000 years to break a 7-bit integer factoring. Okay, here, my question is this. Okay, this is the estimation for the Shor's algorithm. But what if we have a much better algorithm, like only using a single group operation to break a discrete logarithm, or single link operation to break a factoring? So can you rule out this? This is my favorite question. And last year in crypto, together with Yamakawa and Yun, we proved that in the quantum generic group model, discrete logarithm requires a logarithmic group operation. So Shor's algorithm is kind of optimal in terms of group operation, number of group operation. But there are a bunch of many open problems after then. For example, what about the quantum factoring? Can you say something? And another natural question is, in practice, we may have a multiple instance for the discrete logarithm in the same group. In that case, we may ask to find all discrete logarithm solutions, or one out of them. Or we may have some kind of decryption occur to find some discrete logarithm. Then can we find the other solution? This is actually, in the classical setting, this is very studied problems, and actually kind of recently resolved compared to the other classical generic group research, which is dating back to something like 97. Yeah, 10 years ago, multiple discrete logarithm problem shown to be much more harder than discrete logarithm in the generic group model. And actually, the proof is quite complicated. Then what about quantum case? Actually, in the last year, in the same paper, I give a slightly better than Shor algorithm for the multiple discrete logarithm. And it is also practically relevant because it is related to so-called the quantum annoying property for Peik. Anyway, regarding this kind of problem, I answer many. First, I give a multiple discrete logarithm lower bound in the quantum setting. And it actually shows that the previous mentioned algorithm is optimal. And actually, it resolved the another open problem in the previous paper, that the previous paper only showed the lower bound for the prime order, but our lower bound applies for the composite order, like a multiple prime. Second one, I can give a kind of conditional lower bound for factoring, but actually this conditional is impossible to avoid. I think at the end I can say something about this reason why I have a conditional thing. And finally, I also have an alternative proof for the classical lower bound. And all of the same proof use the same tool, and I believe it's much more simple than previous result. Previous classical lower bounds use different technique for different problem, and single lower bound have a different paper. So, okay, this is the summary of the result. And I can explain, even though it's quantum session, I want to explain classical lower bound first. Probably it can give some intuition about the proof. And I like it. Okay, we think about, in this paper, in this talk, we are thinking about the generic group model. In this model, the algorithm Alice have a bunch of group elements, but it cannot. The group elements are stored in the black box and cannot see its inside. So to access or to operate the group operation, it always asks the question to the group oracle. It makes two kinds of operation, oracle query. The first one is a group operation query. For example, what is the group operation for ith element and jth element? Then oracle just answered that, okay, it is GK. And Alice get the GK in the black box. So anyway, it get the group elements, but in the black box. It cannot see the inside. So even for comparison to the two group elements, it needs to ask the equality query to oracle. Let's say Gi and G, ith elements and G's elements are same or not. Then oracle answer, okay, it is the same or not. And algorithm get the answer. It's not in the black box, it's a bit. So this is the generic group model, and as you see, for the discrete logarithm problem, algorithm initially have two group elements. One is the generator and the other is the x times generator. And the question is, how can you find x using this kind of oracle queries? To prove the lower bound, we think about some variation of the algorithm. Whenever we have at least the algorithm, we consider the following simulated version. Yeah, actually, this kind of group elements are anyway stored in the black box. So there is no reason to store group elements in the storage of Alice. So we put every group elements in the other side, oracle side, and it's a just standard method. Instead of storing group elements, we just store the corresponding polynomial representation of the group elements, linear representation. This is because the initial elements are just G and XG, and we only can the addition group operation. So the final elements must be, every group elements must be the linear summation of this. So the group operation goes like this. If Alice want to know the summation of ith and jth elements, it asks the oracle, and oracle compute it. But in this simulated version, oracle never give the answer to the Alice, and Alice just compute the summation of the linear polynomial in his side. So there is no communication from Charlie to Alice here, but the equality query goes in the same way. And in this game, we think about the discrete logarithm problem as follows. Charlie, the oracle or challenger, choose the random x first and want to send x using the group operation. If Alice eventually solves the discrete logarithm problem, he can answer x with certainty or with high probability. Here we assume that Alice is deterministic. It does not change anything, and assume that make a Q queries. Then Charlie, after choosing x, can simulate Alice computation at all. So it compute the first collision of Alice. I mean, first equality query that output 1 of Alice by himself, and then we can think like this. Send this collision to Alice, then simulated Alice do the following. For the group operation query, it compute the group operation as a polynomial. And for the equality query, it just output 0 unless this is the first collision. And finally, it output x using this information. So it is easy to see that this simulated Alice output the correct answer as long as original Alice output the correct answer. Then here our main tool comes in. This is the so-called compression lemma. It says that if we think about the interactive protocol between Charlie and Alice, and Charlie wants to send the n-bit message to Alice. Then whatever Alice do, whatever the protocol is, Charlie must send n-bit if Alice output the correct X. Here, Charlie send ST, and Alice want to output X with certainty. So the compression lemma says that, okay, Charlie want to send a log G bit message, and Alice want to, the communication from Charlie to Alice is just a pair of a collision, which is just represented by two log Q pair, two log Q bit. So two log Q must be larger than log G, and rearranging this gives the discrete logarithm law bound. Yeah, probably some of you think that what is different from this proof and the Schwarzschild lemma proof, but it turns out that the same proof work for the multiple discrete logarithm, which was a bit hard in the previous proof. It goes like this: just choose a random M string and find the M collisions, then send it. Then Alice can simulate the algorithm. Simulated Alice can simulate the original algorithm and output or solution. And the message from Alice to, Charlie to Alice is just the M-pair of collision, which is the Q square choose M. So its information is like this, and rearranging the equation give the tight lower bound. Previously, it was a one paper, and I have a one slide proof. So this is the classical proof, and the other discrete logarithm queries or some things are dealt with easily. Okay, then I can move to the quantum law bound. In the quantum law bound, we need to define what is the quantum generic group model or quantum generic group operation. We can define like this. Let's assume that the indices of group operations are classical for now. Then we have a control bit B. It's a quantum. And as before, we store every group elements in the Challenger site. Then quantum group operation can be computed like this. Alice just compute this and send everything to Charlie. But IJs are classical, so Alice can store it in his brain. Then Charlie compute the group operation and send back B to Alice. So single quantum group operation require a one qubit message from Charlie to Alice. And equally query requires a 1 bit from Charlie to Alice. And interesting thing is the compression lemma holds in the quantum interactive protocol as well. So what we can say is like this. Okay, Oracle, Charlie want to send the log G bit message, and every single quantum group operation or quantum equality query requires a 1 qubit from Charlie to Alice. So Q must be larger than log G. This proved the lower bound for the single instance discrete logarithm. Multiple discrete logarithm is essentially the same, but here we think about a bit more generalization that indices of the group of elements could be quantum. So it could be one among M elements. Then the register, including bit and indices, can be represented by this qubit because B is a 1 qubit, IP and IQ is a log M qubit. Then the proof goes the same way. To solve the multiple M discrete logarithm problem, we need to make Q query that satisfies this. That's it. So it proved that the previous algorithm is optimal, and actually it requires a quantum lemma access to the group elements, and you can show that it is unavoidable in the generic way. Then I can say something about the quantum factoring. Perhaps, yeah, Here I say that every quantum group operation can be done in a single qubit or few qubit communication. So probably it works for the ring operation as well. But this is not true. The problem is in the factoring problem, we usually compute the great common divisor at the end. But we usually think that ring as a Z over NZ for composite n. So this is not ring operation. This is not allowed in the model. So because of this, we need to do something different. Actually, we can give n to the adversary, but in that case, adversary just ignore the ring operation and just factor n. So we cannot say anything. We, of course, think about the ring operation over C, but proving the lower bound in that case, for that operation implies VP is not equal to VNP, which is impossible to prove for me. So we need to think about the ring operation for this. And I proved this. The first one is the order finding problem for this one. This does not require the GCD computation. For this one, actually this is the main step for the Shor's algorithm, require the logarithmic quantum ring operation. And another one is for the Legev style algorithm, it eventually compute the GCD, but one is the final output is relatively small to make a smaller, lower circuit complexity. So I can say some low bound for the Legev style algorithm if it has some smallness property holds. Okay, I have a bunch of open questions. The first one is, can we do the similar thing for the high degree variant like CDH or something like that? Previous work required some algebraic geometry reasoning. I think for CDH, the same reasoning work, but yeah, it's more complicated and I don't know. But for the decisional problem, I literally have no idea. I don't know what to do. And can we use our tool for the other problem like quantum LOM? I'm not sure. It's really hard. For LOM, I think it works. And another interesting question is, can you say something about the quantum circuit low bound for factoring? I think it's a very hard problem because of the reason. Thank you.
Thank you. Any question? So we have some few minutes. Do you want to add something?
I don't want to do so.
So if not, let's thank Minky again. Okay, so the last speaker is Bruno Cabara, and he's going to talk about metacomplexity. Okay, so please
Yes,
start.
thank you. So I'm going to talk about a metacomplexity characterization of quantum cryptography. This is joint work with Eli, Matthew, and Peter. I just want to say that Matthew was responsible for collating this group of complexity theorists and cryptographers. We were on the Simons Institute 2 years ago, and he was going to give the talk today, but unfortunately he fell ill last week, so I'm giving the talk on his behalf. Yeah, good. Yeah, so what is it that keeps cryptographers awake at night? One could probably guess it's the possibility there are protocols and yeah, the primitives are in the end insecure and unsafe because they're founded on assumptions that may turn out to be false. And that motivates the search for the minimal the assumption. We don't want to assume things we don't need for our cryptographic systems to be safe. In the classical case, if you have one-way functions, we know that p versus p is not equal to np is a necessary condition, and showing that this is a sufficient condition has been called by some the holy grail of cryptography. So basing cryptography on the strongly believed assumption that p is not equal to np. This is still an open problem, but there are some specific constructions of one-way functions based on the hardness of some specific problems like factoring or learning with errors and etc. However, when you go to the quantum setting, there are some complications. We know that there's a recent Oracle separation saying that pseudo-random states, which are some of the strongest quantum cryptographic primitives that we have, may exist even if PQP equals QMA, which is the quantum equivalent of P equals NP. So in particular, you may not have one-way functions, and yet you still have quantum cryptography, which means that this classical holy grail is no longer relevant. However, at the same time, in the classical cryptography scenario, there has been a lot of recent progress from the perspective of meta-complexity, which has provided characterizations of cryptography. That means that you have computational problems coming from this field of meta-complexity, which are not only necessary for cryptography to be possible, but also sufficient. So in this talk, we'll give an equivalence between some form of quantum cryptography and complexity theory going through meta-complexity. Of course, this motivates the first question: what is a minimal quantum cryptographic primitive? And as we heard in a talk previously by Justin, this is not super clear. And here there's this image by Eli and Tomoyuki and his co-authors with a lot of primitives, and you see that all these dashed arrows are the Oracle separations that exist between them. And in fact, that all of those, many of those primitives that follow from pseudo-random states are not known to be equivalent. However, if you look at this picture, there seem at least two candidates that seem to fit the bill for being candidates for minimality. Perhaps the absolute most absolute one is EFIs, which are minimal at least in the setting of quantum communication, which are equivalent to bit commitments. But in the setting when you have quantum computation, but classical communication, or also in the setting where your cryptography can be broken by PP oracle, one-way puzzles seem to be the minimal one. And this work will give a characterization of one-way puzzles. So what are one-way puzzles? One-way puzzles are a pair of quantum algorithms, the sampler or the verifier. They're introduced by Corona and Tomer and Stock 24. So what does the sampler algorithm do? It samples two classical strings, K and S, in quantum polynomial time, where key is referred to as the key and S is referred to as the puzzle. The soundness guarantee is that when you sample these strings from the sampler, they pass the verification test with overwhelming probability. And the correctness guarantee is that for every quantum polynomial time adversary, they are not able to, given a random puzzle from the sampler, retrieve a key that passes the verification test. Notably, verification can be inefficient, and as we heard also on the previous quantum session yesterday, there can be a lot of difference between efficient and inefficient verification in quantum cryptography, and this is a primitive that arises very naturally from shadow tomography. Okay, so this is the primitive we're looking at on one-way puzzles, and let's now introduce meta-complexity. Homograph complexity, it tries to give a formal formulation of this notion of information. How much information is there in a specific text? So in the first example, you have this string 101010, and you can think of it, you can just describe it as print 10 8 times. So it has a very short description. Whereas the second one I generated randomly, and there does not seem to be any way of describing the string other than giving you the string itself. Homographic complexity formalizes this notion by saying that the complexity of a string is the minimum length of the program that outputs the string. Some basic properties of the string is that the homographic complexity of the string is at most the length of the string, because you can always hard code the string in a program. Random strings have near maximum homographic complexity, because if you put any limitation of the length of the program, then just by counting argument, there are not that many strings that programs with that much length can describe. And computing homographic complexity is impossible. It's an uncomputable problem. However, the problem we'll be looking at is of approximating homographic complexity. And this problem is as follows. So this gap K problem is the promise problem, where you have to distinguish between strings of homographic complexity at most S and those with homographic complexity at least S plus delta. Okay? And delta here is this gap, and you don't need to output any specific value between S and S plus delta. It doesn't matter. One first observation made by Ilango, Ren, and Santanans, that this can be solved in exponential time on average, meaning more formally that for every polynomial time sample distribution and every superlogarithmic gap, it's possible to compute this gap K problem on the distribution with at most polynomial error in exponential time. And since we're talking about cryptography, you may wonder whether you can replace this exponential time algorithm by an adversary that breaks one-way functions. And on the other hand, you can also ask whether, if you have a gap K algorithm, can you break one-way functions? And this is exactly the meta-complexity characterization that Ilango, Ren, and Santanan obtained in Stock 2020. They show that one-way functions exist if and only if there exists a sample distribution such that gap K is hard on this distribution. The intuition then of this result, or the message, is that the one-way function encodes in itself a probability distribution on which it's hard to compute gap K, and vice versa. Okay? Going to the quantum setting, one simple and first modification you could make is say, okay, let's go and look at quantum adversaries. And so we have post-quantum one-way functions, and then the corresponding problem would be gap K over polynomial time sample distributions being hard for quantum adversaries. And you can get that characterization of post-quantum one-way functions follows simply from the arguments. But what about if you do a fully quantum transformation of this? So not only your adversary is quantum, but also the distribution is quantum sampleable. Now, surprisingly, at least for us, you get exactly one-way puzzles. So one-way puzzles exist. This is our result, if and only if gap K is average case hard on quantum sample distributions for quantum algorithms. And okay, the message now is that one-way puzzles are encoding this hard distribution and vice versa, and hard quantum sampleable distribution. Okay. Some other takeaway messages for this is that this is giving you further evidence of the centrality of one-way puzzles in this QCCC setting. Besides all the the combiners, the hardness amplification, and other nice properties that one-way puzzles have, they seem to be a natural generalization of one-way functions. They seem to be also embodying some fundamental hardness because they are exactly capturing the hardness of gap K in the quantum setting. And it seems also to give you the property that insights about one-way functions can be also applied to one-way puzzles. If you put in some work, and also gives you the construction of this microcrypt primitives or fully quantum primitives from an assumption that does not seem to imply classical cryptography. One other takeaway from this, and I think, is that this also brings you or highlights the importance of the gap K in quantum cryptography, because then you're seeing that the big difference between this quantum mania and count crypt worlds becomes just the difference between the hardness of gap K over classically sampleable distributions and quantum sampleable distributions. So potentially you could, that's probably impossible, but potentially you could say that if it's hard to compute gap k over quantum sample distributions, and it's also hard to compute gap k over classical distributions, and then you would get one-way functions from one-way puzzles. This is not what we expect, but this shows the importance of studying this problem for cryptography. So how do we obtain this result? The crucial intermediate step, as in the classical case, is going through probability estimation. So what is this problem? So let's DB this algorithm that's sampling classical strings. Let Px will denote by the probability that x is sampled by the distribution. And the probability estimation problem is that when you're given a sample x from the distribution, you want to output a delta estimate of Px, okay? An estimate within a delta factor of Px. And the first thing we show is that if you can break one-way puzzles, then you can do probability estimation. How is that done classically? Basically, what you're going to do is use the one-way function to do the following. You're going to, the sampler is taking classical strings, randomness strings, to fed into it that it uses to sample strings. And you are going to hash this randomness strings into hash buckets. You're going to take a random hash bucket and try to invert. If you have very few hash buckets with very high probability, you're going to find a randomness string that maps to x. But if you have like a higher number of hash buckets, then you're going to not find the randomness strings that maps to x any longer. And the threshold at which you no longer start to be able to invert this one-way function is when gives you the estimate for Px. Of course, the difficulty of generalizing this to the quantum setting is that for quantum samplers, the randomness is inherent to the distribution. You cannot hash out its randomness as it's done here. And this is where we bring also this paper that was mentioned before of Kaimin, Eli, and Matthew. And one of the results that we're going to use is that this equivalence between one-way puzzles and distribution of one-way puzzles. And the takeaway here is that if you can break one-way puzzles, then not only can you find a key that passes the verification test, but you can sample from the conditional distribution of keys conditioned on the puzzle that you received. Okay? So how does that allow us to do probability estimation? Now we're going to construct the following one-way puzzle. You are going to sample an x from the distribution that you want to estimate probability of. Going to sample a hash function. The key is just going to be x, and the puzzle is going to be the hash function and the hash bucket of x. Now what's going to happen when you try to invert h of x? It's like you're looking at the correct hash bucket where x is. And if you have too few hash buckets, then like x is going to be there with too many things. And then when you invert, because you're inverting distributionally, you're not going to see x very often because other things map to it. But as you increase the number of hash buckets, then you're going to isolate x, and then you're going to see only x in this distribution. So, again, looking at the threshold, when you start seeing x, gives you the estimate for Px. We can also use probability estimation to compute cap k, just like in the classical case. We just show like this quantum coding theorem, which is basically saying that probability is a proxy for Kolmogorov complexity. Like if you have low probability, then you have quite high Kolmogorov complexity. So just by using probability estimation, you can compute Kolmogorov complexity. So this completes the first part of the characterization, that you can compute Kolmogorov complexity by breaking one-way puzzles. And now let's do the other direction. The other direction also uses the result of theirs, where they show that if you have one-way puzzles, then you can construct this this thing I call non-uniform entropy gap generator, but this is not standard terminology. It's just what it is a quantum polynomial time distribution whose entropy is sufficiently far from maximum, but at the same time is indistinguishable from uniform by quantum polynomial time adversaries. Now, by applying the same coding theorem and from the previous slide, we can argue that if your distribution has low entropy, then with a noticeable probability, the strings it outputs have low common graph complexity, and thus common graph complexity can be broken. That entropy gap generator can be broken by common graph complexity, and thus we can break 1A puzzles. So I just want to say that there's 2 concurrent works. So Krohn and Tomer stuck this year, also show an equivalence between probability estimation and 1A puzzles, and also Taiga and Tomoyuki also obtain a characterization of gap k, of 1A puzzles via the average case hardness with gap k, but the proofs of both 1 and 2 are slightly different than ours. So some open questions. First, can we characterize this with a problem that has a worst case complexity bound? So gap k, we know it can complete expression time on average, but we would like to, it'd be nice to have a problem that does have an actual worst case complexity bound. Can we characterize other primitives, EFIs, one-way state generators? Can we obtain strong average case hardness? So we only showed, I didn't mention this too much, but the notion of average case hardness that we're using is weak average case hardness. So this oracle separation between one-way functions and one-way puzzles does not rule out the possibility of constructing one-way puzzles from the hardness of a meta-complexity problem in QMA. We cannot make that characterization, but it may still be possible to make that construction. And that's a nice open problem. Thank you.
Thank you. Any question? So is there any example of meta-complexity problem in QMA?
Yeah, so one meta-complexity problem in QMA that I don't think would probably characterize this is just you can make a notion of time-bound and quantum common graph complexity. So it's like you want a uniformly generated quantum circuit, just generated in polynomial time, that outputs your string with probability at least 2/3. So you want to decide if the given string has a small description in this notion of quantum common graph complexity. I think this would even be QCMA. Yeah.
And is that also believed to be outside of BQP?
You're asking if this notion of if this meta-complexity problem would be outside BQP?
Yeah.
I guess so. Yeah, would be very surprising. Yeah.
Other question? Okay. So if not, let's thank the speaker again.
Thank you.